Welcome. The goal of this video is to help students build up their confidence in dealing with situations where the problem is in an inclined surface. After having a chat with a couple of students, I realized that they are not confident in where to place the angle of inclination in the free body diagram. Some of the students have done a good job of placing it right, but I get the feeling they're not confident as to why the angle goes there, or they don't have the reason. So the goal of this video is to address that. I have two approaches. The first one is more intuitive, and the second one will be analytic. So I may truncate this video into two pieces, but let's start off with understanding at least is there a way we could define what we mean by an incline? Well, I do believe you know what an incline is. However, I would like you to think about it in a slightly different way than what you probably have seen. I like to think of an incline as a deviation from the horizontal. So imagine I have this surface. I'm looking at it side on. So this is a flat surface. If I wanted to construct an incline from this surface, let's choose this point as our starting point, I would need to draw a line like that. This line here is an incline, and if you look at this line, it is a deviation from the horizontal. And we could measure the amount by which we have deviated from the horizontal, and that amount would be the angle of the inclination. So let's say theta were equal to 30 degrees. That would tell me how much does this surface deviate from the horizontal. You may do this when you are in your treadmill. Sometimes you may have a treadmill that's flat, but because you want a challenging workout, you might lift up the surface, the pad or the belt, and you might be running up the incline to give yourself a bit of a good workout. So imagine from now on, think of an incline as a rotation. Maybe let me write that down. Think of an incline as a rotation from the horizontal plane. Okay, if you are comfortable with this definition, of course I have to admit it's a functional definition, it's not all-inclusive, but it captures the essence of what an incline is. So let's go on now to the intuitive approach of understanding where the angle should be placed. On this page I have two coordinate systems, one is blue and one is red. These coordinate systems, in particular their horizontal directions, they are both horizontal or flat. Hence here they have a zero angle of inclination. I can prove that because I can select the blue one, for instance, and try to superimpose it over the red, and notice the red lines align with the blue lines. The blue y and the red y align, and the red x and the blue x also. But let's do something to the blue one. Suppose I were to take the blue one and I were to deviate it slightly. There I have it deviated. Now if I were to try to impose or superimpose it, that is, place the blue over the red, what do you notice? What you will notice is the red y no longer aligns with the blue y. And the same goes, the red x no longer aligns with the blue x. Why? It's because I've rotated the blue coordinate system by a certain amount of angle. And let's call that angle theta, the angle of rotation. If we call it theta, now I would ask a very simple question. By how much has the blue line deviated from the x line? Well, it's going to be the same amount by which I've rotated the blue. So I can happily say that angle is theta. But notice, not only are the x's no longer in alignment, but the y's are also no longer in alignment. The question is, by how much are they offset? What is the deviation between the blue y and the red y? Actually, it's going to be the exact same amount. This angle here is also going to be theta, the angle of deviation from the red, between the red and the blue. Actually, this is true not only on these positive points of the axes, it's also true on the negative sides. The angle here will also be theta, and the angle here will also be theta. Because that angle tells us by how much do these coordinate axes no longer align. That's what that rotation has done. It has put them out of orientation, out of alignment, and the amount by which they no longer align is the same amount as the angle of rotation or inclination. Okay, I hope by this you can already see how this would be applicable. So let's pull up an example. Here, I have two scenarios where we are dragging a box by applying a force T across a flat surface. But I should say flat horizontal surface. It's not enough that it's flat, but it's also horizontal. And the second situation is we are dragging the box, this time around, on a flat surface, but this surface is no longer horizontal. It's actually rotated by an angle theta from the horizontal. Let's draw a free body diagram for both of these scenarios, and let's do the exact same thing that we did in the example over here. Okay, the free body diagram looks like this. And this one over here is when we are dealing with a horizontal surface. We have our T, that is our tension that we're applying to drag the box. This is the normal force by virtue of the box being supported by a surface. And since we're doing this on some planet, I guess let's stick to Earth. So there will be a force of gravity. Now, let's consider the situation when we're on an inclined surface. On an inclined surface, notice our normal force is no longer in line with the gravitational force because the surface is no longer horizontal. Our surface is tilted, which means the force of support is perpendicular to that surface, so that's our normal force. But the force of gravity hasn't changed orientation because gravity is always pulling you toward the center of the planet. So the force of gravity will still be downward, and now our tension is up the incline, so its orientation is that way. And all of this is due to the fact that this incline or this surface is rotated by an angle theta. Now comes the punchline. Let's try to superimpose these guys. And for a little bit, the diagram is going to get cluttered, but I'd like to ask you, consider the red lines and the blue lines, and in the comments, tell me by how much does the blue line deviate from the red line. Okay, so let's impose them, and there they are. I have superimposed them, and you will notice that the blue line, deviates from the red line. And the question is, by how much do they deviate? And also on this side, the red line deviates from the blue line. By how much do they deviate? If you find that answer, if you know that answer, that will inform you as to determine where to place this angle, theta of the incline, in the context of your free body diagram. I will stop the video here and I will continue with the analytic approach in the subsequent video. Okay, see you in the next one.